I want to ask you a couple questions about things you know about random variables. Does anybody have a definition for what a random variable is?
It's a function.
It's a function. So, has a property. So that property says that I can map back to the original space that produced my random variable. So, and I can basically measure its probability in that original space. So if I take two dice, for instance, I could ask, what's the probability that I roll something that the sum of the faces is 7? Okay, so that can happen in a lot of different ways. I can get a 2 and a 5, 4 and 3s, 3s and 4s, 5s and 2s, 6 and 1, 1 and 6. And I can measure what the probability of all those individual elements are that make up 7, and I can add them together. And so I can invert back to the original space. So there's a lot of technicalities there, but I think we all get the idea. And so functions of random variables are also random variables. And so what's a random variable? Does it mean that it's random in nature? No, it means this mathematical thing that we can invert back. And so once I define a full probability space and how I can union and intersect everything and complement, I get those rules, and I have a full description of probability. And so if you ever take a measure theory class, you'll understand that perfectly. And you'll be able to confuse people with it, but it really is a simple concept. Let me ask a quick question about the dice that I'm holding. If I roll them, and I add up the faces, that's a 7 right there. That's a 7. There's 7s today, I can make some money. So my question is are those rolls independent of each other? So is me getting a 7 independent of me getting a 7 on the first trial?
Yeah.
What do you think? So independence, right?
Not
Okay.
perfectly because physics.
Okay, right. So I can appreciate what you're saying, that it's like there's these minor nuances out there, and we're going to get into a big philosophical debate. So let's avoid it. So I have fun with that too. I think it's fun to think about. But maybe independent. Let me roll again. I have an 11. I'm making money. So I have an 11. So let me roll those dice again. On the ground, no problem. We'll let it go. A 5 and a 6 and 11. You might think that I'm a master roller. So I'm at least honest about reading the faces. An 11. So maybe these dice aren't independent. Or maybe we don't understand what the concept means. I have a 7. I'm pretty good. What just happened? I won millions of dollars in Vegas. And so let me ask you again, are those dice roll independent? Did me rolling the dice for a little while help you to learn anything?
Are they fair dice?
What do you mean by fair? Of course they're fair.
Do they have 6 sides of different numbers on each side?
They have 6 sides.
What are the numbers
Seven.
on the dice?
I don't know. So, and you don't know either, which is my point.
Yeah.
So you made an assumption about the dice that I were rolling. And so I want to ask this question, was this true for the dice roll, or at least the sum of the dice? So I'll just say sum is equal to x1 plus x2. So this is die 1, this is die 2, and this is the sum. And so the question is this true? Probability of, I'll say, x2, this is my second, I'll say this. Wow. S2, second roll, given S1, is this equal to probability of S2? There's other ways to write this down. These are equivalent statements. Probability of S1, this is my first roll. So I'm putting an order on things. And S2, joint probability does this factorize? So this is the description that most people know as independence. So is this true? These are equivalent statements. So if you understand the definition of a conditional probability, so it's the joint divided by the margin. If you don't know that, you haven't taken probability, and this is going to be a really hard class. So, but do I learn? And I could end up building this up a little bit more if I had the whole sequence of things. Let's say I rolled it 7 times. If I looked at the first 6 rolls, do I learn anything from it? And so this statement right here says you do not learn. So if I roll it once and I see what's going on, you can't see, but it's an 11. So let you see my dice soon. So question is that true? So I rolled it once, it's an 11. What do you think the next roll is going to be?
7.
Maybe 7. Anybody else have another guess?
11.
Maybe 11. Oh, you guys are smart, right? So 11's win. So something you learned, right? Would you have answered differently if I were rolling your dice? You carry dice, right?
Always.
Always, right? So statisticians always have trick coins and weird dice and things like that to exemplify points. But this is not true. This statement isn't true at all. So, because I'm able to learn from the data. So let me ask the question again. When I roll the dice, this random variable that I'm looking at, the sum of the faces, are those in sequence independent of each other? Ben?
So they are independent given full knowledge of the dice and not independent given you don't know about the dice.
Thank you very much. And there's a distinguishing point there. And so if I told you the probability of the faces, if I gave you that full description of probability, then if I conditioned on it, these statements would be true. So now you can look at my dice if you'd like. Can't do this too close to anybody because these don't fool anyone.
You'd probably get shot in the
Yeah.
casino.
Oh, so I'd probably get shot, geez. So probably shouldn't play with these. These are not even like loaded dice. This one has 5s and this one has 6s and 2s. So there's only 2 possibilities here. And so if you don't know that and you roll it, you're learning about something. And so IID data, you might say these are IID, but you need a full description of the probability distribution. So identical and identically distributed, and you know what you're talking about. And so in statistics, we're always trying to learn. So this isn't true, but another statement is true. And I'll write it down like this. This is conditional independence. Probability of sum 2 given sum 1 and p. This is the probability of dice. Okay, so this would be a probability of 1 through 6 on each one of the dice. You can think of that as a big vector or 2 vectors if my dice weren't the same. But you get to know it. So these are the parameters in the model. This is what Ben was saying, full knowledge of the dice. So the parameters of the model are the probabilities of observing 1 through 6 on each one of the dice. And you have to know what those probabilities are. Usually, real quickly, we assign those as 1/6. And if it's 9 o'clock in the morning, I can get you to still think it's 1/6 after a couple rolls, but it won't fool you for long. You'll ask the question when we see those things. Think you're tricking me, of course I am. So this right here is equal to probability S2 given P. So this bar always means given. Everything to the right, the way I use this bar, everything to the right is given. So given that I know the probabilities of the dice, I don't learn anything by rolling everything. So there's no knowledge to be got. So these are conditionally independent. And I like to really harp on this conditionality thing. So because this does not factorize, the data doesn't. However, if I conditioned on P in all the statements, then everything would factorize. So let me just write that down to be more clear about it. The factorization happens conditioned on knowledge. So for probability of S2 and S1 given P, so these are all the probabilities of the faces on the die, is equal to the probability of S2 given P times the probability of S1 given P. So everything gets conditioned. If you know knowledge, you use it everywhere in the equations. And so the factorization happens given P. Now just tell you something practical. What a Bayesian will do, or a likelihoodist, is we'll product this together, we'll plug in our data that we see and treat it as a function of P, and then use that to estimate P. It's a likelihood function. And so we can build that up conditionally. So if I tried to integrate P out of this equation, you would not be able to disentangle S1 and S2. It wouldn't factorize. Given knowledge of P, you have the factorization. That's an incredibly important thing. So let's just take this home a little bit more, build up some tools and some glossary. Let's talk about sampling procedures. Okay, so I think everybody understands that the factorization happens with respect to P. Let me say one more thing about it. In math class, when you learned what independence was, they taught it to you using sets. Okay, so in set theory, the original definition is okay, no problem. But we use data. And so no data in the world is independent of each other. Data has something to do with the other data. But given full knowledge of the state of the universe and all the driving parameters, then you have no extra knowledge. What you're actually doing in statistics is you're estimating what your knowledge is with the data. So that's what we're always doing. So how do we learn about the future if we have IID data? No data can tell you about the future. What you're learning about is the parameters, which help you to forecast. Okay, so the data is not independent. Data with modeling assumptions. That's when you have independence. So I want to point out in my examples that it didn't matter which order I saw everything in. So if your data is IID, you can shuffle the order. The order doesn't matter. The converse to that statement is not true. And so I'll ask you to do a homework problem pertaining to that. Okay. So let's talk about some other sampling right here. So I've got my hat, and I had these specially crafted. I had these dice specially crafted, and I had these things specially crafted in such a way that while they all look a little bit different from each other, they have exactly the same volume and area. And so the probability of me grabbing this blue one and this blue one in the hat are exactly the same. And I had these machined precisely so that this would happen. Okay. So what I'm basically saying is these are IID draws. Please don't question that. So close enough. So I did not have them specially machined. So, but you know, if I reach into the hat, my point is these two blue ones, what's the probability that I grab one over the other? Let's presuppose that they're equal. Okay. So Ben, got it? So Ben's gonna say It's not an IID distribution because they're slightly different shapes. So close enough. Okay, I'm gonna take some blue ones. Right here, some number of them. I've got 5. And I'm gonna take some red ones. And I've got 3. Okay, so I let you know that in advance. And I'm gonna put those in. So let me just write down what I said. So, red, there's 5 of these. And then the blue ones, oops, I did that backwards, right? 3 and 5. So some basic concepts in probability land. I'm gonna give those a shuffle. My random number, setting the seed in my random number generator right now. So, always give it a shuffle. If you don't shuffle your computer periodically, the results are gonna look less than normal. They're random. So let me just ask the question this. What is the probability that I'll say my first draw is equal to a red? What do you think? Yeah. No trick question.
3/8.
Yeah, it's 3/8. And the probability that x1 is equal to a blue. Full description of the probability space once I tell you there's no other possibilities. Okay, those things add up to 1. So probabilities do this. If you've written down all the events, you're always positive 2. So let me just ask a question real quick. Chin, what do you predict I pull out of the hat? What's your prediction? Blue. Okay. So you got blue. So very good. Excellent predictor. I'm going to reset the random number seed. Give it a shuffle. Chin. What do you predict I reach in and grab? Blue. So you're good. So blue one. Let's do it again. What do you think? Blue. Very good. So one more just for good measure. What do you think I'm gonna grab? Still thinks blue. Always blue, huh? You're wrong. So red one. So just for good measure, I like to repeat myself a lot. What do you think? Blue. She likes blue. Very good. Okay. So, wasn't able to fool Chin on too much. Pretty good predictor. I think she got 5 out of 6 correct. Okay. Now I'm going to do something different real quick. I'm going to empty my hat. And I'm going to do some stuff real quickly. Change the distribution and the seed. We're going to get rid of this. That just changed. So I've changed the probability distribution. And you don't know the probability distribution this time. So you don't get to actually observe it in advance. Chin, let me ask you a question. What do you think I'm going to pick? Red. Why? Just because you like red, right? So look. So let me put it back in real quick. So I replaced it. And so we got a red. I'm just going to write these down. So first one, x1 is red. Give this a shape. What do you think, Shin? You think red? You looked up there for a second. It's interesting. So, blue. So, let's write it down. X3.
Red.
How come?
Red.
How come? Flip. So I'm going to put it back in. Just write it down. Blue. What do you think? You're getting good at this.
Red.
So now red. Interesting. So let's go for it. You turned out to be right. So this one's red. I'm gonna stop here and ask you why you did that. So you were right. And so you could say because I was right and I knew I was gonna be right. So that would be amazing. Let's think about statistics for a second. Once I've seen that right here, should I use this information in forecasting that? Is this important to decide what I should pick right here?
Yes.
I think so. So in the first example, it wasn't important. And so when I told you this, you didn't need to look at the data. So I would have thought the logical guess right here, because I had seen 2 blues, would be, I would guess blue. That's what I personally would have done. So I've seen 2 blues. What am I actually doing? I'm starting to hone in on the probability. So I'm able to use the old data to estimate what the true parameters are in my bag. The parameters being the probability of red and blue. How many red things are there versus blues? And so I'm going to try to estimate them as I see data. And if I kept doing this over and over again, I would start to get a very good understanding of what the true probabilities were. But with just a little bit of data, I don't know. So I can reach in there again, I get another blue right here. And so I've got 3 to 2. Not a lot of information. You know, it's about balanced, it seems like. What we could do is we could keep doing that over and over again, and eventually you'll estimate whatever this percentage is that was in the bag. In reality, we never actually get to count this. All we ever get to see is the data. And so it's still the same mechanism. I was sampling exactly the same with replacement. I wouldn't change the distribution. Every time I shuffled everything, I had the same distribution. In my 2 experiments, I had different distributions, but within those 2 experiments, same distribution. So it was independent sampling, and under knowledge of the parameters, it all factorizes. But what a statistician is trying to do is estimate those parameters. So, and then use that to forecast. So the point is that the data itself, while this factorization happens, if you want to write it down this way, same as the factorization, the data itself has information about the future through the parameters in the model that you're estimating. So that's a difference between independence and conditional independence. Does anybody have any questions about that?
What would you have guessed if you're sampling without replacement? If you got a red, blue, blue?
Yeah, so let's do that a little bit. So without replacement is a little bit different of a scheme, and they talk about it in the book. So let me just ask this other question. So we did everything sampling with replacement. But we can do it without replacement. Let me ask a couple questions about this. Let me give you some knowledge first. So I'm going to go for 5 blues and 3 reds again. Get rid of these. The hat is empty. So we're back to that original distribution, 5 and 3. So 5 and 3. Let's just ask this question. What's the probability that x1 is equal to a red?
3.
3. So I can grab one. and I take it out of the bag. That's blue. So the first one that I actually saw was blue. Let me ask this question. What's the probability that this is equal to a red? 3 seconds. Right here. Let me give it a shake. Take out something, and I get another blue. That's good. So the point is, in this, is these probabilities change every time I do this. This is not IID sampling. So, not IID sampling at all. Something very, very different. Let me ask you a question though. If I were to do this, let's do it maybe once more. Or not. So, I have a hole in the hat. If I did this, let's just say this happened. So let's just say that I ended up getting, say I dragged from the hat again and I ended up getting a red. Let's just suppose that happened. I'm a little bit dumbfounded if I ended up just seeing this, and if I asked what's your probability of the blues and the reds, you'd have a hard time answering. So the simple fact that we hadn't seen a red give us like some inability to answer that question. Got to observe it to want to say something about it. Now that's almost true. There are methods that you can use to estimate something that you don't observe, but be careful about that. It's probably driven a lot by your assumptions. And so if I saw this right here, this vector, and if I asked you, what's the probability that my original bag, I would pull a blue out, what do you think that probability would be? So if I just asked the question, what's the probability of red and blue in the basket in my hat, what would you answer if you saw this? What's that?
2/3.
2/3 probably. I think it's still a good answer. It doesn't seem to matter if I sampled with or without replacement. So, but the distribution changes a little bit when you do that. And so if n were really, really big, my denominator were really big, these two numbers would be really close to each other. And they would look and feel almost like IID sampling. And so almost IID sampling. And scientists usually do sampling without replacement. So they don't want to go and sample the same person twice in their survey or something like that. It's actually a slight statistical mistake. But it doesn't actually change any of the marginal probabilities of anything. And it's almost IID, so usually people say it's all right. Let me just tell you what I mean about marginal sampling. The margins remain the same. So let's just set the problem up a little bit differently. This is in your book. Say you have a collection of unique data points. I'll call it X1, X2, X3, all the way to Xn. So I get n unique data points. And each has probability 1 over n in the original sample. So they're all equally weighted. Let me ask you a couple questions about this. The first question's real easy. What's the probability that x1, so this will be my first draw, is equal to xi, any particular value in this set. Xi is just some one of these data points that I've picked from that vector. 1 over n. So this is just 1 over n. Doesn't matter if I was sampling with or without replacement on the first step. We're going to sample without replacement, or I'll say without replacement. And I want to ask this question. What's the probability that x2 is equal to any particular value, xi? So what this says is that if I'm going to go through this sequence, I'm going to go through and I'm going to grab two particular values. I'm going to grab the first one here. Then I'm going to remove that thing from my collection of data points. And I'm going to try to figure out what the probability is that on the second draw, I observe some unique value in the vector.
Are you able to observe x1? Are we observing x1?
This question on its own, yeah, exactly. So if I'm observing x1, so this question is different from that. This says that I didn't observe because I didn't write it down. So if I were trying to be explicit about that, I would write this. Probability of x2 is equal to xi given x1 is equal to some other value. So these statements are different. And so Elise is being really good about this. Explain your notation to me. Make sure I understand what I've conditioned on. And so I'm actually asking this marginal question. What's the probability that x2, the second draw, is one of these particular values? What do you think? So let's just be clear about this. So I've got my numbers in here. Let's say I were trying to guess about this. What's the probability that my second draw is that number? It's also 1 over n. So this is 1 over n. Let's just make sure we understand why that's true. So the margins have the same distributions, but each draw in the sequence, we're changing the overall distribution. So how do we figure this out? End up just writing down probability that x2 is equal to some particular value, xi. How we do this is we look at the probability that x2 is equal to xi given x1 is equal to xj. Times the probability that x1 is equal to xj. The j doesn't have braces on it. They're not being ordered, they're just elements in my set. And so what I want to average over is j. J goes from one to n. So this right here, this is the joint probability of the two values in the sequence. x2 is equal to, my apologies, that's not ordered, xi, and x1 is equal to xj. So each element in this sum is a joint probability. This is called marginalization. So if I want this margin on the second thing, I need to condition on all the possibilities of the first thing and account for their probability of occurring. So this part we already know. This is 1 over n. First draw being any particular value is 1 over n. This part, we know, looks like this. It's 1 over n minus 1, because I'm going to remove something from the set. And this is if xi is not equal to xj. Since I've removed it from the set in their unique values, there's no probability that I can sample that same value twice. This happens with probability 0 if xi is equal to xj. So one of those things can't happen. If I've already grabbed xi, I don't get to grab it again on the second draw.
So is that probability x1 equals xi given x1 equals xj? No, if x2 equals xi.
So I'm just conditioning on whatever this xj was right here.
Right. What's on the left? Like, in that-
What's this one? The second draw being an xi value. Some other value. And so what's the probability that it's any other value? I removed something from the set, 1 over n minus 1. What's the nth possibility? What's that data point that I've removed already and I can't see it on the second draw? So if I sum over all of this, how many non-zero things do I see in here? N minus 1 of them. They each have probability 1 over n minus 1. This is probability 1 over n. So this looks like sum 1 over n minus 1. So, and I'm going to write this down over all the i's not equal to j. There's only n minus 1 of those times 1 over n. So this is going to be n minus 1 over n minus 1 times 1 over n, which is equal to 1 over n. So your intuition's quite good. So the margins are preserved. And I can also say in sampling without replacement, it doesn't matter which order I actually see things. I can shuffle it all around. And so in that original example where I'm grabbing red and blue beads out of everything, if I were to see 2 blues and 1 red in the first sequence, it wouldn't matter which order I saw those in. I can shuffle them. So shuffling is called exchangeability. I want to point out that exchangeability is a data concept. I don't need model to think about that. I don't need to think about what the model is. It's just, it doesn't matter which order I see this data in, it's exchangeable. However, independence is a model-related concept. I need model and knowledge of P to do the factorization. And so independence is a modeling assumption. It's not a quality of the data itself. So data itself is not independent. It's independent with model in hand. Do you understand the difference? So independence is not a quality about data. It's a quality about data and model. Exchangeability and shuffling everything is a statement about the data itself. So let me just say a fact about that. If data is IID, independent and identically distributed, so distribution doesn't change every time I sample it, everything, then data is exchangeable. Does that make sense? Think about it just if you're more mathematical and you think about what you always do with IID data, you product something together. And in that product, when I'm using that for inference, it doesn't matter which order you product things together. Yeah, I can shuffle them around and I have the same inference. So if you're used to working with IID stuff, you're always producting together sampling distributions. And it doesn't matter which order you product them together. Ben?
I'll admit I'm somewhat confused here. You're saying we're given a collection of unique data points, and then we're asking the probability that x1 equals another xi. What do we mean when the data points are unique here?
They're all labeled uniquely, so I can distinguish each one of those n values in the vector.
Okay.
This is simpler than you think. They're just unique. Think of them all as a different color, and I can label them. Or I put the label x1 through xn on them. So they're labeled, and they each have probability 1 over n.
So if all of the marbles are a different color, for example, then why is the probability that x1 equals xi 1 over n instead of delta 1i? like, if you have two different drives without replacement, then you'll never get two of the same color with
Let's do
different
this.
drives.
Okay, I've got two values right here. So my collection is just x1 and x2. Let's do this with three things. So I don't divide by 0. I have three unique values. So now I'm going to say I can distinguish those two blue things. One of them is metallic-ish and translucent, and this one is opaque. So I can tell those apart from each other. This one is red. Okay. So let me ask this question again. What's the probability that I pick red on the first draw?
1/3.
1/3. So I grab randomly, can't see anything, I grab some value. So I pull it out of the set. Now here's my distribution. I grab this opaque blue one. Okay, so now I'm going to ask the question, what's the probability that I grab red out of my not replace sampling distribution?
So you haven't picked the red yet?
I picked this one.
Yeah.
I actually did it.
Good.
That's removed. So I'm giving you an explicit example. What's the probability that it's red?
1/2.
1/2, you got it. That's what I mean. That's the 1 over n minus 1. Okay, let's go the other possibility.
Well,
Let's just, hold on, Ben. Let's just do this. What's the probability that I pick red on the first one?
still 1/3.
1/3. Okay, I'm just going to cheat.
Yeah.
Red. Okay, let's say I pick that with probability 1/3. What's the probability that on my second attempt that I grab red?
0.
0.
But my point is the probability that x1 equals xi for another. Wait, what's xi here? Is xi a specific?
Xi is a specific value.
Oh, got it. I was confusing with x parenthesis I.
Cool. Right on. So the parentheses are orderings. Yeah, sometimes notation is the killer. Once you understand what it says, usually things are pretty simple. So understanding and being able to read mathematics or ask the right question, that's the hard one. Okay, good. Hopefully we've all got this. Does this make sense, this fact that I told you? If the data is IID, then the data is exchangeable. So if I give you data with model and I say that the model factorizes as a product of of just the individual elements, then I say it doesn't matter which order I see the data in. Did you prove it? Proof's pretty easy. So I have to give you a mechanism for how I actually pick the parameters that underline the data, but I'll give you any arbitrary mechanism. So I'll call it pi theta. So I'm going to say the xi's themselves are IID from fx given theta. So theta are my parameters. And I'm going to tell you how I pick theta. Now you might think I can pick it in lots of different ways and you don't like dealing with theta as a random variable. But if you don't like that and you want to make it fixed, just let this be a delta function. That I plug in some particular theta into everything with probability 1. So I'm giving you a random mechanism and you can make it deterministic if you want by placing mass just at one point. So if you have a predetermined theta. So I want to know this. fx1 and x2, I want to prove this. fx2 and x1. You can extend this up to any permutation if you want. So if I'm just looking at two data points, then any permutation is just a shuffle of those two things. So I also want to show the joint distribution over n data points can be shuffled around. I'll let you work on that proof yourself. Let me do the one with just two data points in it. So we want to prove this. We know fx1, x2, given theta, is equal to fx1 given theta times fx2 given theta. How do I know that?
Assuming that it's in.
Because I told you. And that's what it means mathematically. If I change this stuff, I don't have any influence on the other thing. And so, how do I get this? These are different statements. This one is conditional on theta, and I want to make a statement irregardless of theta. Regardless of what theta is, I want to show that I can shuffle this thing. So the probability distribution of the data doesn't depend on the order. They're equal to each other. So if I have an equation like this, how do I get rid of theta? It's only one thing you can ever do. One thing. So moving from conditional distributions to margins. So this is a conditional distribution on x, and I want to get rid of the theta, so I want to marginalize it out. That's the only mathematical tool in town. You can't do anything else. So how do I get this right here?
Integrate.
Integrate. So fx1, x2, given theta, the only time I can integrate over theta is if it's a random variable. You are not allowed to integrate over things that are not random variables. So this right here says theta's fixed. Now I'm going to account for my mechanism for choosing theta. If you want to make it deterministic, that's okay. You can put a point mass value on any particular theta you want and 0 everywhere else. So I better upgrade that to a random variable, and I'm going to integrate over theta. This thing right here is fx1 given theta times fx2 given theta. And I can change the order of that. So I learned a long time ago, I can multiply by things in any order. I can commute these things. So that's integral fx2 fx1 given theta. So I'm just going to recombine these things after I shuffle the order of them. Pi theta d theta is equal to fx2 x1. So why does everything exchange? It is because of this shuffling of the thing. That's the mechanism that this commutes. Let me ask you a different question. So these are just very basic data concepts. If data is exchangeable, is the data IID? Just saw it in one direction. This proof tells me if it's IID, because I can factorize things, change the order in the product, and then recombine everything, that it's necessarily exchangeable. Is the converse true? Is it true in that opposite direction?
No.
So not necessarily. So it's the answer. If you'd like an example, think about sampling without replacement. So sampling without replacement, we already kind of figured out that's exchangeable. Doesn't matter which order you saw the draws in. You can just use those and still look at the count frequencies to estimate the true probabilities. But the joint distributions themselves were not IID because the distribution changed every time I get a sample. So I'm going to ask you to prove that, but you can prove it almost using blue balls and red balls if you'd like, that sort of concept. So we'll come back next time and we'll show you an actual tool using all of these sampling procedures for estimating unknown parameters or distributions over any statistics that you want without having to do any math. And so just by using our computer to subsample from data sets. So independent, identically distributed sampling with replacement is the fundamental building block of a tool called the bootstrap. So we're going to start out with that next time, come in and talk about the bootstrap, look at some examples, see when it works and see when it fails. Thanks, you guys.